So welcome to lesson number 6 on interference and diffraction, where we're now going to do the second part of that lesson, 6.2, which is explaining diffraction. So make sure you have your notes downloaded so you can be an active learner and work along with me. Let's go to the section on explaining diffraction. Well, what is diffraction? You can hear people talking around corners. And diffraction is the spreading of a wave around a corner or through a gap. Here's my definition here for diffraction. So it's the spreading out of a wave as it passes through a gap. Let me explain diffraction using water waves. So here's a water wave. And it's going to pass through an obstacle in the sea. So here I am looking at my water wave side on. There's the crest, there's the trough. You know what the wavelength is. The wavelength is the distance from crest to crest. That's lambda. Instead of looking at my wave sideways, let me look at my wave from above it. Let's say I'm in a helicopter and I'm looking straight down. Everywhere I see a crest, I'm going to represent it by a continuous straight line. That line there will represent the high point of the crest of my wave. Here's another crest. And here's another crest. If you wish, you can draw the troughs in between as broken lines. So here's the trough, and I draw a broken line in between. Here's the trough, broken line again. And of course, when I look at my wave from above, the wavelength, lambda, will be the distance between two continuous lines. That there represents lambda. Okay, so this wave is moving to the right past this obstacle. And what would you expect to happen when it hits the obstacle? Well, the obstacle will block this part of the wave down here, and this part above the obstacle, that's able to pass through. So this wave will pass through like this. But you know, something looks a little bit weird there. You have a situation where you've got waves bopping up and down right there, and right beside them, the water is totally calm. Well, we know that water molecules affect water molecules beside them. So when these water molecules are bopping up and down, they're going to cause the water close by to bop up and down. So you will see a wave that bends around the corner. That's called diffraction, spreading of waves around corners or through gaps. Let me now progress the story. Let's go on to the next part of the diagram in your notes. So once again, here's my set of water waves, and I'm going to pass them through now a gap in two obstacles. The size of the gap, this size here, I'm going to call D. And of course, the wavelength, that's the distance between two crests or two continuous lines. That's lambda. In this particular example, you can see the size of the gap D is far greater. There is a symbol for is greater than. And far greater, I can do something like that. So D is far greater than lambda. Now, when that happens, you do not get great diffraction. So once again, what happens? That part of the wave gets blocked, that part of the wave gets blocked, and the middle section is able to pass through. It'll pass through like this. But once again, like I said in the previous diagram, you don't expect to see nice high waves right there and totally calm water beside them. Water affects water, so there is a bending of the wave around the corner. But it's not a huge amount of bending or a huge amount of spreading out. We would say actually the diffraction is quite poor. So if the size of the gap in the obstacle is far greater than the wavelength, then I can say that I get fairly poor diffraction, fairly poor spreading out through the gap. Now moving on to the next part of the story. Let's say that I squeeze the gap. I make the gap smaller. So now in this particular diagram here, here's my gap. The size of the gap is called D. The wavelength, of course, is lambda. And now in this particular diagram, I've made the size of the gap D approximately equal to the size of the wavelength lambda. Now, when you do that, you now get very, very good diffraction. You get fantastic spreading out of the waves. So when the waves spread out through that particular gap, they spread out as lovely circular waves. So there's a great spreading out. That's fantastic diffraction. So now let me continue the story. Let me now move on to a situation where I send my wave. There's the wavelength, of course, lambda. And I send it now at an obstacle that has two gaps in it. And the size of each of the gaps is approximately equal to the wavelength. That means that the wave spreading out through each gap is going to be really, really good. I'm going to get a really good diffraction. So from the first gap, the waves are spread out into lovely circular waves. In the second gap, the same thing happens. Lovely circular waves. Those two gaps are actually the sources of the same kinds of waves. They're called coherent sources. I'd call this source 1 and source 2 because the waves coming out of each gap are identical in every way. They have to be, don't they? They're originating from the same wave, so they're going to give rise to two sets of waves that are identical. So I'll say that S1 and S2 are what are called coherent sources. Now, the previous part of the lesson, we talked about interference. Now you've got two sets of waves that are identical. And what happens when you have two sets of waves that are identical? They will interfere. So these two waves will start merging together. You're going to get points along those waves. You see here, crest, overlaps crest, overlaps crest. And along those lines there, you're going to get what's called CI, constructive interference. You're also going to get points in between. I didn't put the troughs in there, where crest will meet a trough. You're going to get points, therefore, that will give rise to destructive interference. You know what you're going to see? You're going to get a series of high waves, CI, and no waves at all, destructive interference. You're going to get what's called an interference pattern of high waves and no waves at all. Let me return to our notes. So this particular diagram there explains what I'm talking about. You know, interference of waves following diffraction. Setting up an interference pattern. That is fantastic proof that something is a wave motion. So if they say prove sound is a wave motion or prove light is a wave motion, that's what I want to show. When we did that with light, it was actually a famous scientist called Thomas Young, who carried out the experiment. And when he sent light through two gaps, he ended up getting bright and dark images. Bright images were CI, and dark images were destructive interference. When the experiment is carried out with sound, CI, in terms of sound, would be a nice loud sound. And when it comes to DI, you'll get no sound or very low sound. Let's have a look at a demonstration experiment to show that light is a wave. So as I said, if you can show interference of waves following diffraction, those two things together, then that's excellent proof that something is a wave motion. This is a very important demo experiment. It's one that they like asking quite a lot. And it was carried out by someone called Young. So it's called Young's experiment. So let me explain it to you on the board. So here I have an obstacle with two gaps in it. The gaps actually have to be very, very small if we're talking about light. Light has a very, very small wavelength. We're talking about something like 1/10,000th of a millimeter. That's how small. So these gaps have to be extremely small because it's only when the size of the gap is about the same size as the wavelength that you get this really good diffraction. So we're going to send light at that obstacle with two gaps in it. We're going to use monochromatic light. Chrome means color. Mono means one. So we're talking about one color. And when you're talking about one color, you're talking about one wavelength. So like pure red, for example. So I send it at the obstacle with the two gaps. When it hits the obstacle, the waves will spread out into nice circular waves. You're going to get really good diffraction. Over here, I've got a screen. And what happens is the interference pattern is set up on the screen. The first thing that happens, of course, is diffraction takes place. So it's always diffraction first. Then the two sets of waves spread out and they are coherent waves. These two gaps here represent coherent sources, S1 and S2. Now the two sets of waves interfere. So that's interference. And an interference pattern will be set up. What will the interference pattern look like in the case of light? Well, everywhere constructive interference takes place, you will see a nice bright image. That there is a bright image, and that bright image there represents CI, constructive interference. And then in between, you're going to get places where you see absolutely no image whatsoever. That will be a dark image or no image. And that's where DI took place. So you're going to have an interference pattern, which is a series of bright and dark images. I mean, that's excellent proof that light is a wave. Because if it wasn't a wave, if light is just a set of tiny particles, what would you see happening? The light would just simply go through the two gaps and leave two spots corresponding to the gaps there and there. But that kind of interference pattern is fantastic proof that light is a wave. Let me go through that experiment in our notes. It's very important that when you do a demo experiment, you have your three headings there. What's the apparatus? What's the method? And what's your observation or conclusion? Well, the apparatus, a label diagram will suffice for the apparatus. What's the method? Well, basically, in your method, just one or two sentences, but try and capture all the technical terms. So a source of monochromatic light is passed through two slits S1 and S2, which act as coherent sources. I'm getting all my nice words in. Waves spread out, that's called diffraction. And merge or combine, that's called interference. That's your method. What do I observe then on the screen? I observe bright, that's constructive interference, and dark, that's destructive interference images, are formed on a screen. So Young's experiment is proof that light is a wave motion. You see, make sure you have your three headings in there when you give the explanation for your demo experiment. Okay, so that's the end of this particular lesson. In the next lesson, we'll go on and solve diffraction problems. Thank you.